This conference will
Condensate,
now be recorded.
condensate is just what happens when steam condenses in the radiator and returns to the boiler. That's the condensate. The dry return would be up here until it gets down to about the water line of the boiler. You would consider that a dry return. And then when it gets into there, it's a wet return. And this would be the equalizer line coming off the boiler. So as you produce steam out of your header into the riser into the header before it takes off to the system, some would take off to the system, and the remaining condensate would then return back the equalizer line. You've got a gauge glass on here. That is a really important item, you guys. You're going to want to, that's a real good clue as to what's happening in the boiler. It'll tell you the level of the water in the boiler, whether it's too high, too low. You can see whether you have impurities in the water, whether you've got oil in the water. So the equalizer line and the gauge glass is a very critical part of this. The Hartford loop was developed back when boilers were blowing up. The Hartford Insurance Company came out with this. It's a way that if we do not return water to the system through the wet return, that the boiler would not continue to fire. And if it did before this, the water would drain back out, the boiler would continue to fire, and they would just blow up. They would get so hot they would just glow and then explode. It can be very dangerous. Again, this is the header. You have a low water cutoff, usually on boilers, which isn't shown in this. Main vent, usually found at the end of the mains on both one and two pipe steam systems, gravity returns. One pipe steam, which is what this typical picture is showing. There's just one pipe going into the radiator. And that's pretty basic. If you walk into a house, the first thing you want to do is look at the radiator. If there's just one pipe down below the radiator on the lower side and a vent about halfway up on the opposite side, that way you know you're in a one pipe steam system. If you have two pipes, either just with a trap on the outside or a return elbow, that would be a two pipe system. So you know what you're looking at before you go down to the boiler room. Pitch is important. You want to try and pitch your headers so that any condensate that forms in here will go down the equalizer line. Pressure controls, we'll go through those a little more. Pressure sensing safety devices to shut off the burner when the steam pressure gets too high. You got pump returns, which you'll usually find that on a commercial boiler, but you can definitely find them on residential. There are a lot of houses in the Cincinnati area. I'm sure if the people listening up in Cleveland, I know there are a lot of big houses up there, probably have our Weil-McLean LGB boilers, which is a sectional boiler. And a lot of those, because of mandated government regulations, the steam chest has been decreased. So the steam separation is done in the header. And that's why so you'll have a pumped return to bring the water back. Radiation, any kind of device that allows steam to give up its heat. The radiator valve and the radiator vent, those are pretty self-explanatory, I would think. The radiator valve allows the steam to come through. In a one-pipe steam system, you want to have this valve open completely because steam has to pass over the top of the condensate that's forming along the bottom of the radiator. And we'll go through that more in another slide. So you've got the steam chest of the boiler, the steam pressure. In most residential systems, you'd probably want to operate somewhere around a half-pound cut in on your pressure controls and a pound and a half cut out. That's a good standard setting. And we'll go through some of those different options later also. You've got traps, then you've got two-pipe steam, which is where steam flows in the radiation while condensate and air flow out of the radiation through two separate pipes. You got the vertical supply riser, which is pretty self-explanatory. The water line of the boiler, it's different for every boiler, but it's you'll usually see that standard water lines would be about a 1/4 inch above the bottom of the gauge glass. And then there's the wet return, which on older systems, this is one of the items that tends to everything in the system will eventually collect in the wet return. And over a period of time, you'll get all the mud, all the rust, anything that's accumulated in the radiators of the system. It will all collect there on the wet return. And if that is clogged, then that leads to freshwater makeup, which is a killer for cast iron boilers. So that's some of the basic terminology to know when you walk into a boiler room. And we can provide that a copy of this with the definitions if you guys need it. We can have Larry do that at the end of the program or get it to you afterwards. Okay, so what are the basic concepts of steam heating? You got 3 basic concepts. Whoops. Okay. Well, the 3 basic concepts to steam, you have to is steam up, air out, and water back. You have to produce clean, dry steam, and dry steam is defined as having 2% or less of the water entrained in the steam. The function of a clean boiler and proper piping per manufacturer's instructions are also critical to produce clean, dry steam. The second one is to remove air. Steam will not enter with air present because steam is lighter than air. So you need to have a vent that's working in order to allow the air to escape to allow the steam to come in. And then we have to get water back, which means we have to have unobstructed return lines. All right. So here we have a typical boiler with water filled up. It's turned off currently. We have the radiator, and then we have the air vent. With the burner on, steam forms at the highest temperature. It's released at the water line, assuming we have a clean boiler and there's no oil on the level there. And then steam releases at the water line and the vent starts to open. As the steam pressure builds up, condensate starts to form on the side of the pipe and steam flows towards the lower pressure of the boiler. So with steam, the pressure goes from higher to lower. So the higher pressure is formed at the boiler, the lower pressure is in the radiator, so the steam flows towards lower pressure. And then the air flows out of the air vent. The vent closes. We get good warm heat out of the radiator. The steam condenses on the cool surfaces of that radiator, and then it starts to flow back to the boiler. So there are 2 types of residential steam systems. The one-pipe steam system, which, as we explained, only has 1 pipe going to the radiator. And then we have a 2-pipe steam system, which has a supply. Usually in older systems, it'll be at the top of the radiator, and it's either a steam trap or a return L, because in some really nice homes, what they did was they just put a return L here, and then they moved the radiator trap down into the basement. So I've seen some really nicer areas in Cincinnati that you can go through the basement and all the thermostatic traps are down there for ease of maintenance, so you didn't have to go disturb the homeowner if you were working on a steam trap for the radiator. So this is a 1-pipe radiator. We got to look inside. So we've got that single riser coming into the radiator valve. And again, this valve must be left completely open so that we can have steam passing over water entering the radiator and condensate flowing back through the same valve. So since steam is lighter than air, it'll rise to the top of the radiator, which is why the air vent is usually located down lower on the side, because it's going to push the air in front of it down to that radiator to vent. As the steam condenses on the side of the radiator, it rises through the valve and water flows back through that valve. Condensing steam causes a slight vacuum that draws in more steam, and the air is forced down and out the vent. The radiator is usually only full of steam on the coldest days or on the very first startup at the beginning of the year. And then the vent would close once it encounters steam. And as the steam condenses small quantities of air, it releases small quantities of air. The vent cycles open and close to remove all the air. And that's a typical one pipe radiator. Okay, as we go to a two pipe radiator, it's basically the same setup. We've got the vertical riser coming into the radiator valve at the top of the radiator, and then a thermostatic trap at the opposite side at the bottom of the radiator. With this type of setup, the valve doesn't have to be completely open. In fact, you may be able to go through and help balance the system by closing off some of the hotter rooms, opening up some of the cooler rooms to try and balance the flow of steam. And so, as we said, since steam is lighter than air, it'll heat across the top and force the air down and out of the trap. As it condenses the side of the radiator, it'll go through that trap and flow back towards the return lines. Pitch is important here. Over a period of time, or if people have decided to remodel their rooms, sometimes they'll disconnect the radiator, lay a new floor, and then just repipe the radiator. You need to make sure that that radiator has some type of pitch. It doesn't have to be great. It just has to be pitched so that the water will flow towards the return side of the radiator. If it sits in there, you can get what's called water hammer, and we'll discuss that a little farther down. Condensing steam causes a slight vacuum that draws more steam into the radiator. The trap is open to air and water. As soon as the trap experiences steam to the little disc in there, it closes to keep the steam in the radiator. But once the water starts to cool, the trap will open up and remove let the condensate return to the system. Here's just a fun fact about radiators. If you paint a radiator with any kind of paint, I would recommend a automotive paint because it can allow heat to escape. But if you paint a radiator, it will reduce the output of the heat that's available to be produced by the radiator. And the weird part of it is, if you paint it a second time, it will return to the original rating. Don't ask me how it happens. That's more of an engineering question, and I definitely am not an engineer. But I thought that was a pretty neat fact that you can paint it once and it reduces the heat. Paint it again, it'll bring it back to the original rating. Okay, so Weil-McLain puts out something called the radiation reference tables, and these are available at Winstall, all the Winstall sites. We can get some sent to you if you would like to. You can find them online on weilmclain.com. They do show it there. And they go through all the different types of, or the three basic types of radiation that are out there now. There is a book put out by Dan Holohan called EDR. And in that, it's the term for EDR is the equivalent direct radiation, or the amount of square feet that the radiator is sized for. His book is called EDR, which stands for Every Damn Radiator. And trust me, you look through that book, it has almost every kind of radiator that I've seen in the 38 plus years that I've been doing this. So it'll go through, it'll identify the style of radiator. So there are usually three different types. The column type radiator, which has a thicker column to it. It's usually about 2.5 to 3 inches thick as you look at the side of the radiator. A tube type radiator has a thickness of approximately inch and a half thick, and then there's what's called a thin tube radiator, which is 3/4 of an inch or so thick. So that's one way to determine what type of radiator you have. So in order to figure out how many square feet or how many BTUs this radiator can put out, You need to measure the height and the width of the radiator, count the number of tubes across the end section. So if you look at this one, it has 1, 2, 3, 4 tubes. Then you would go across the radiator and count the number of sections to determine the square feet of the radiation per section from the appropriate table and multiply by the number of sections. So this is the first page. These are the old style column type radiators. So you can see if you found one. And again, this is measured from the foot down here of the radiator to the very top. I've been in some situations. Maybe you got a piece of carpet here, and you think you're down at the actual foot, and you take your measurement, and you come up with 37.5 or 36. If it's a column style, I would then just go up to the 38. If it has 3 columns, you would go over here, circle the 5 square foot per section, and then you count the number of sections. So if you've got a 5-section radiator that's 9 inches deep and 38 inches high with 5 square feet, you would have 25 square feet. And then you would multiply that by 240 to get the amount of BTUs of steam that equates to, or 150 for the amount of BTUs that water equates to. And then again, this is the tube type radiators. This is the same situation. If you got a 36 high, 5 tube, you got 5 square feet, 5 sections, you got 25 square feet. Pretty straightforward there. And then this is the thin tube, same situation. They generally, if you purchased a new radiator today, this would be the type of radiator that you would get. And purchasing a new radiator is a very expensive option. And this is a plug for Winstall. We keep used radiators at our Spring Grove site. If you need a radiator, get us the dimensions and we can tell you whether we would have a used one in stock that we could pressure test for you. There are some that you'll find in garages and some basements. I've seen these wall type sections. They can be hung on the ceiling of a basement. Normally you'll see them in a garage. Same with the sectional types. And again, these are just sized by the height, which would be normally on these. They're pretty typically 13.5 inches high, and then 17 section wide by 3 inches thick. And if you've got one that's 17 inches, that's good for 5 square foot for one of these. Usually you'll find these connected together. You'll find a series of them, 2 or 3 of them connected together across a wall in a garage. Okay. So we have pressure controls for boilers. And so what this is, a pressure actuated high limit safety control for steam heating boilers. The steam system pressure depends on the size and condition of the pipes and the amount of steam flowing through them. You can assume the dead guy that sized this house you're in installed the system based on his calculations of 1 ounce of pressure loss per 100 feet of pipe in a 1-pipe system, double that for a 2-pipe system. So as I said previously, the rule of thumb on these standard pressure trolls, and these pressure trolls come with all of our Weil-McLean boilers, steam boilers that we sell, and most manufacturers' steam boilers will come with 2 of these normally. One is an operating control, which is what you would set at that 1.5 psi cut in and 1.5 psi cut out for the 1 ounce differential, which what the fitter sized it for back in the 1800s or whenever the house was built. So you'll get one operating control and then one that's a high limit control. So you would set the high limit control at probably about 3 psi. So if you reach that, it's going to shut down the burner, and you've got some issues. You need to go and do some investigating to the system. The sensitive pressure actuated diaphragm expands or contracts, moving a lever mechanism that operates a snap switch to make that control. Okay, The other option when you get into one of the larger homes that were built in the 1920s and 1930s, those houses were generally being fired with coal boilers. So if you go down in one of those big old houses, you'll probably see somewhere near the boiler a coal chute from where they used to load the coal. And with those types of systems, they were designed to operate on ounces of steam. They usually had larger pipes, and at night the owner would bank the coals in the boiler and allow them to operate on very low pressure throughout the night and keep heat going in the system. So the vapor stat provides operating control and automatic high limit protection for vapor heating systems, and there are a lot of them out there. Paul Train has one, and you can generally find out whether this was the house you're at was originally a vapor system because the valve on the top of the radiator is a really odd looking valve, and I'll have to get one of those for the next presentation. But basically, it's got like a lever handle with a pointer and a graduated um, rating on it, so you can open and close it where you want. And most of the vapor systems were designed with those radiators or those radiator valves as a balancing control type of situation. But a lot of times you'll go into homes now and they will have a couple of, maybe if they've got 15 radiators in one of the big houses that had these vapor systems, maybe 5 of them still have the original vapor valves on them. And because of failure throughout the years, people have gone back and put standard radiator valves on. So the way to try and make that system work is what you need to do is close off all of the new style radiators, radiator valves, and then fire the system, and then just go back and slowly crack each one. And you probably won't be opening them very much more than maybe a quarter turn in order to try and balance that system. That otherwise, if you do run into that and they're having problems with the radiators with the vapor style valves on them, it's probably just a good idea at that point to change them all over to standard radiator valves. You can still run the system in vapor. That's not a big deal. But it'd probably be a good idea to change those out. Oh, before we go to this, um, next slide, I apologize for hitting that, Larry. That's our second question. The standard range on a vapor stat control is 0 to 16 ounces, and you want to try and do a 4 ounce. Um, Usually, a good set is a 4 ounce cut in and an 8 ounce cut out. So um, that's what we have. So, Larry, that's our second question.
Okay. I think I'm sharing it right now. There it is, guys. Question number 2. What is the range of a standard vapor stat control? And there's your choices. And you can see the one that's highlighted is the one you're going to need. Okay. So now let me pass this back to you.
Let's see.
And you're going to need to start where you left off. So don't, if you even had to close it, you probably didn't even need to close it, but let's just get you back.
Okay.
All right. And I'm making you the presenter. You should be good. Okay, just hit that. It should pop right up, right where you left off.
Mm-hmm.
Just hit the PowerPoint down at the bottom there.
Yeah.
There you go. All right, now go up to under the word home, hit from current slide.
There we go. Maybe by the last time we get the third the third question, I'll figure that one out.
Yeah.
Okay, so that was our second question. All right, so this is the one pipe steam vent. So this is the vent you're going to find lower down on the one pipe steam radiator. you'll generally find two types of one pipe steam radiator vents, and we use the Hoffman 1A, which is an adjustable vent. It has a 1 through 5 number system on the top, and those numbers correlate to, in theory, temperature. So you can, with that type of one pipe steam valve, you can somewhat try and help balance the system. If you have a one room that's heating really hot, you would turn that valve down to a 1. And then if you've got others that are cooler, you would turn those up to 5. And that would allow more or less air to come out of the vent. So here it is as before the boiler fires. It's just filled with air and open to the system. As the boiler fires and steam starts to fill that one pipe steam radiator, it will fill the radiator with steam, which the float inside there is filled with it says in the picture, a volatile liquid. The steam heats that liquid up, which expands that float until it pushes the pin up into the port to close it off. And it will keep it closed until the radiator starts to cool, and it'll keep it closed while it's cooling, because we have to get that water evacuated out of that one pipe steam valve. So it will stay closed until the water drops below the vent, and then it will reopen back to the first page. What's kind of important about these valves is that let's go with the 1A valve, and that has a maximum. If you look at the either the literature, the box, or the vent itself, the 1A vent has a maximum 10 psi operating pressure. So obviously no one pipe steam system should be operating anywhere near that, but it has an operating pressure of 1.5 psi. So if you show up and the pressure control is set, say, at a 2-pound cut in and a 4-pound cut out, which a lot of times people try and do that. They think if they're not getting enough steam, they're not getting enough heat in the house, well, we're not producing enough pressure. So let's go down and raise the pressure on those controls and see if we can get more steam out to the house. The opposite is, in fact, is true. Dan Holohan had a mantra just called "turn it down, crank it down." That's, crank those operating controls down. So again, the operating pressure is 1.5 psi on a 1A valve. If you show up and your pressure control is set at a 2-pound cut in and a 4-pound cut out, it'll start up fine on the first cycle of that boiler. So as it starts up, the cycle vent closes because it's set at 2 to 4 pounds. The vent will never reopen. The system has to cool completely for the pressure to drop below 1.5 pound to reopen. So that's why generally half pound, pound and a half is the rule of thumb for most residential steam systems if you're not using vapor or a vapor stat. So this is the same operating principle here. This is the main steam vent that you would find at the end of the main, usually a Hoffman number 75. There's some vents out there called Gorton, like the Gorton fish sticks or the Gorton fisherman, Gorton. They make a number 2, I believe it is, air vent, which it's a round air vent. And the number 2 air vent will pass the equivalent of 4 number 75 air vents. So a lot of times on larger homes where they have long runs of piping, you want to try and evacuate that air as quickly as possible. And sometimes you'll see one or two 75s on a tree and they're still having issues. At that point, I would probably recommend to you to find, and Gorton will not sell to distributors. They only sell online. So you guys can go directly online and buy a Gorton vent that would do equal to what a number 75 Hoffman, four number 75 Hoffmans. So it'll evacuate the same amount of air that four 75 Hoffman vents will evacuate. But it operates on the same principle as the smaller 1As or number 40s, which is a non-adjustable one-pipe steam vent. The 75 sits inert, all open to the air, allowing air into the system. As the steam rises in the radiator in the main line, it will hit that vent and heat up the volatile mixture inside of that float, which will expand to close the port and keep it closed as. Oh, my battery's running low. Hang on, guys. All right, I think we should be good now. Sorry about that. So it'll keep it closed while water is still in the main. As that drops below the entrance to the vent, it will then return back to its inert state. Okay, let's see. Larry, do we want to take a short break here, or you want me to
Yeah,
continue?
that's fine.
Yeah, I
We're
think this is probably a good place to stop.
all right. Are you good with tell you what, it's 5:20. Why don't we say 5:35? That'll be 14 minutes. Okay, guys? We'll see you in about 14 minutes. 5:35. Thanks. Shift F5. F5. Marty's there. Crying out loud, Larry. Harry's there too. Well, I'm going to say Devin Johnson. This one shouldn't be there anyway. Signed up twice. Or do I have two Johnsons? Kyle Johnson and Devin Johnson. All right, fix that. Six. Okay, we're back. We hope everybody's refreshed and ready to go. What I'd like to do now is pass this back to Jeff. And well, let's see. Yeah, I've got my screen up there. Okay, Jeff, I'm going to pass this back to you. Let me see how if I turn on your microphone again. Here we go. Trying to unmute you. Yep. Can you hear me, Jeff? Okay, turn your mic on. Your microphone is off. I'm trying to undo it, but you're muted, Jeff. We're not hearing you. There you
I'm
go.
there.
All right. Hit PowerPoint and then hold the Shift key down and press F5, and you'll pick up where you left off.
Very good. All right, here we go. We're on to steam traps. Steam trap theory. All types of traps have in common the purpose of stopping the flow of steam at some point in the system. The three basic traps that you should encounter in just about any steam system would be the water seal trap, thermostatic traps, and float and thermostatic traps. So what you have here is a water seal, and generally you will only see water seals on one pipe steam systems. You can find them on some two pipes, but it's not common at all. So it's mostly one pipe steam. So the air vent is normally, the air is normally vented above the water trap with a main vent. So that would be the number 75 or the Gorton that we talked about. You go to the end of the main, you'll find one or two or multiples of those, depending on how quickly they're trying to get the air out. The water seals the steam in the supply main at the balance point of the vertical pipe. So basically what that is, condensate from the system flows back through the wet return. So it'll feed steam down to that point, and that steam pressure also helps force the water back into the boiler. And again, with this type of trap, if you are having issues with freshwater makeup where you're adding a lot of water to the boiler it's generally because we are not returning the condensate, and the most common cause is clogged wet returns, because this right here is the lowest point of that system. So any crud accumulating, anything that comes back into the air vent before it shuts out, all that is going to get gravitating down towards the bottom. And eventually your, say, 1.5-inch return, wet return is so clogged, you got about a 1/2-inch diameter opening for condensate to pass. And then you can run into all kinds of trouble. So generally, if you have to go to replace, if you're called in to replace a gravity return boiler, always look at the wet returns before you just go stick another boiler in there. And that's true of any boiler replacement. You want to take a walk around the boiler room and see what you can see. See what kind of issues may be causing that boiler to fail. I mean, the last thing a homeowner wants to do is spend thousands of dollars on a new piece of equipment and have it fail in a couple of years. Because trust me, especially in Cincinnati, Ohio, the city of Cincinnati chlorinates their water, and chlorinated water is deadly to cast iron. Cast iron sections are manufactured with a rust coating on the inside of the section for protection. And as you add fresh water to a system, you start to skim away. Every time you add fresh water, you skim away a little bit of that rust. And eventually, once the rust is gone, then you'll start skimming away cast iron. So the two big things with a new steam boiler installation, one would be to find some way to flush out or visually inspect that wet return. And the other is more recent, is putting some type of filter on your city water. Again, this is Cincinnati. It may be different where you are. You need to check with your waterworks to see if they're chlorinating the water with chlorides or chlorine. That is what kills that, and oxygen are two big killers for cast iron boilers. So probably put some type of bag filter, some type of chloride or chlorine filter on the water supply to the boiler, and then clean out the wet return, and that should increase the longevity of the new boiler. Okay, the second type of steam trap you will find on usually two pipe steams at the end of the radiators. And this is called a thermostatic trap. And you can see that inside of the thermostatic trap is a bellows, an element. And this is typical, this is almost the same type of element, or the material inside of this element is the same that's used in the air vents. So it's a volatile liquid. The trap stays open with no heat to the system. As the steam comes to the radiator, it will fill that trap, and the heat will expand that element inside of there to push the pin down to close the trap. So it will keep the steam in the radiator to heat the room until it has used up all of its capacity, and then it will turn to condensate. And once it turns to condensate, it'll cool that element down, cool the liquid inside that element, which will then retract, pulling the pin back and allowing condensate to return to the return line back to the boiler. Now, there is one other place that you may see a thermostatic trap, and that is a lot of times in old gravity systems, or just in systems that have really long runs. At the end of the main, what they will do is mount one of these thermostatic traps up on the top and connect it to the return line. So what it will do, it'll act as an air vent in that situation. So it's going to vent that air a lot faster in the main, allowing steam to get out to the system quicker. And hopefully we can shut the boiler down on a limit control as opposed to a low water application. The perfect cycle is to go off on limit as opposed to low water cutoff. If you go off on low water continuously, it's time to take a look at that system and see what's going on with it. So that's the second type of trap, thermostatic trap. The third type of trap you'll see is called a float and thermostatic trap, and pretty evidenced by what you see. You've got a float ball down at the bottom, and you've got the thermostatic trap up at the top. And what happens if you have to go convert an old gravity steam system? Again, with old gravity steam systems, the boilers that were in those systems were these huge American Standard or Red Flash, or there's all kinds of different manufacturers from the 40s and 50s, and those steam chests were huge. And in some of them, you could probably fit a small current today's boiler inside the steam chest of the old boiler. So they didn't have any issues with extra water coming back. That steam chest could handle it. But when you convert to a pumped system, you can't have that steam coming back to your boiler feed tank. Excuse me. So you have to put you have to trap the ends of the mains when you're converting from gravity to a pumped return. So on like an LGB boiler, we put a Hoffman VBF boiler feed unit in there. We would have to put that boiler feed unit in to collect the condensate, because if all the condensate would go back to the smaller steam chest LGB, it would flood the boiler. So in order to keep that from happening, we put the tank in to collect the condensate, and then we put a control on the boiler called a a pump controller that would then activate the pump on the boiler feed tank whenever the boiler is calling for water. So it operates in the same principle as a thermostatic trap. It has a thermostat up top and the float down at the bottom. As the steam enters, it causes the fluid in the element to expand and pushes the pin into the top of the trap, keeping steam in the line as opposed to returning down or going down the return line and energizing all of that wet return. And then if it fails, the steam gets to the pump on that boiler feed unit, which the pump usually has a seal in it that's rated for 225 degrees. And if you start putting injecting live steam into that boiler feed tank, it will probably start rocking and rolling, and it will burn that seal up. You'll have a leak, and you'll have to go back and repair that pump now, which is never a fun thing to do because you generally have to drain the system to do that. So as the thermostatic element expands, it keeps the steam in there, and then the steam starts to condense in the main, and as it does, it fills up the body of the floating thermostatic trap, which causes the float to rise, pulls the pin from the bottom of the trap to allow the condensate to return to the main. Okay, so those were three types of the steam vents that you'll normally incur. So back at the beginning, we were going through all the different definitions of what you've got there. We come to the sight glass, which is installed on every steam boiler. Every steam boiler you encounter will have a sight glass. And again, normal operating sight glass levels when the boiler is turned off is usually about halfway up the sight glass. So we've got good clean water. We've got the sight glass. This is a cold sight glass, and this is what it should look like. If you don't see any water in the glass, we've obviously dropped too low, and we need to find out why we're not filling. Usually when it drops to that point, you have a control on the boiler called a low water cutoff. And what that is designed to do is stop the boiler from firing when there is not enough water in the boiler to produce steam. So it will shut the boiler down until we can get enough water in there to allow it to start to fire again. If it's too full, we've got that problem of maybe we've got too much condensate coming back somehow, or we've got sluggish condensate return. So what can happen with this is, let's say we go through a cycle on the boiler, but because it's a real long run in the boiler in the basement of the house, and maybe it's a 80, 90-year-old house, some of the return lines start to sag, which causes a delay in getting the condensate back, or there's some obstruction in the return lines that's slowing down the condensate from getting back to the boiler. And so maybe the boiler goes off on low water, and so the feeder comes on, feeds the boiler up to about half or so again. And then as soon as that shuts down, we get that slow slug of condensate that comes back, and then it raises that boiler line up over above the top of the sight glass. So too full is not good too. We need to find out why that's happening. And generally you'll go out into the system and see what's going on. So, and then you can run into what's a dirty sight glass, and that is any type of rust or oil that has accumulated throughout cycles, and it tends to show up in the gauge glass. So we've got a dirty gauge glass. That means we have to either skim that boiler, and there are skimming procedures out there. We can get you information if you need that, or there's I think it's misnamed. It's called the 1 hour boiler cleaner, or we sell a product called dry steam. It takes longer than an hour. There's a procedure to do that also. It can take quite a bit of time to do that. So but it is necessary because we can't produce clean, dry steam if we've got a dirty boiler. So this is a working boiler. This is working sight glass. So when a when the boiler starts to operate, the water level's obviously up here about halfway. And when you see a good working steam boiler, that water in the sight glass will just slowly drop as the steam is going out into the system. If you see it start to bounce, if you see that the water in that gauge glass start to bounce as it's going down, that means that the water inside of that boiler is going to look like a wave pool up at your local water park. It is going to be rocking and rolling in there. And that's generally a sign of a dirty boiler also. If you've got a skim of oil on the top of the boiler, um, then it's not going to allow good steam to be produced. It'll kind of plop out. There's a way to check whether you've got oil in your water. You'll need an old pot that you're never going to use in your house again. And you drain a little water off the boiler drain, and you put it on the oven or on the stove, and you heat it up to boiling. And when you do that with a standard pot of water, you notice that steam gently wafts off the top of the water. But if you've got oil in there, it will produce a skim on the top of that water, and it'll be like steam bubbles popping up out of that water. And that's what causes that water line to bounce. And again, if it's bouncing like that in the gauge glass, it is just rocking and rolling in that boiler. And we got to clean that boiler. Okay, so we're on the basic theory of the steam cycle, simplified to three steps that we've talked about. The path of steam up, the steam is generated in the boiler and rises up the supply pipe to the radiation. So that's our steam up. Again, we have to produce clean, dry steam, which is less than 2% of entrained water. And that is what we are shooting for with every boiler cycle. The path of air out. So steam up, air out. The air is pushed ahead out of the piping and the radiation. It's pushed ahead of the steam. Steam replaces the air in the piping and the radiation. Steam will, again, as I said earlier, will not go where air is. So we need to make sure that our air vents are working properly so that we can get the air out of the radiator. Again, this drawing may not be the best because on a one pipe steam, the valve's up here and the vent's down here. On two pipe, it's usually the thermostatic trap, but this gives you the basic idea that we need to vent the air out of this radiator before steam will enter it. And then we have to trace the steam, the path of water back to the boiler. Steam condenses to water in the piping and the radiation, and then the water flows back to the boiler through the return line. Again, into that wet return, which would be, and we don't show the Hartford loop here either because this is just a basic drawing, but we need to make sure that that wet return is clear of any obstructions to allow timely return of the condensate. So we've got the near boiler piping now. And depending on how big the boiler is, the near boiler piping consists of the boiler supply outlet, which are these tappings on the top of the boiler, or on the Weil-McLean boiler, they come out the side. And you've got the boiler supply outlet, the supply risers. These would be the riser, and you want to put a swing joint in here because steam can leave a cast iron boiler at roughly 1,700 feet per second. And if you do not have a swing joint in there, which the swing joint allows for the expansion of the steam in the piping, if you don't have that swing joint in there, what happens is it puts tremendous pressure on the connection to the boiler section from the supply outlet, from the riser, and you can crack that section top because, again, that steam comes out there incredibly fast. So changes in boiler design through the years have affected the near boiler piping supply. That's what I was getting to before with the larger steam chest boilers made in the 50s and 60s that, due to government regulations, mandated more efficient boilers, which made the boilers smaller. The steam chest inside the boiler is smaller. So now most manufacturers rely on this header as a way to help. Whereas in the old big thick boilers, they did all the steam separation in the steam chest. Now we need to help the steam separate using the header. So it is vital that you follow the manufacturer's instruction on the pipe sizes required for your risers and your headers. Because without that, we will be sending wet steam out to the boilers, so it'll be pulling as its steam condenses in that main. If it's not big enough, it'll take water out with it every time it fires. And then that can cause low water conditions and other problems throughout the boiler. So that's why we want to produce that clean, dry steam. And part of that is the proper pitching and the proper near boiler piping. We want to pitch it back so that any condensate that does form in this header will go to the equalizer line and drop back to the boiler. You'll notice here, and this is typical of an LGB, but it's probably pretty typical of almost every boiler out there. We need 24 inches minimum from the bottom of the header to the water line of the boiler. We need that to be able to produce that dry steam in the header. We need that distance. It's been proven by engineers that that's the distance we need. So when you're going to repipe, if you need to do a new header, that's a critical dimension you need to be aware of. You need to find the water line. With an LGB boiler or sectional boiler, it's 33 7/16 from the floor or the housekeeping pad you have the boiler mounted on. So it would be, so at 33 7/16, we had 24. We're right around 58 inches. So if you make sure the bottom of your header is at least 58 inches from the floor, you should be good. The other dimension is, depending on what boiler you have, the LGB wants 4 inches, the smaller EG, H, Weil McLean boilers, EG boilers, they require a 2-inch below the water line as to where you make your Hartford loop connection. And again, that's just that's a safety feature. On pumped returns, this Hartford loop is not critical, but I would highly recommend that you still put it in there. Having double safety on low water is never a bad idea, but it's not required by code if you are pumping your return back to the boiler. And again, this Hartford loop needs to be either installed with a close nipple between this elbow and this T on the equalizing line. It has to be a close nipple, or this has to be a street 90 that will thread directly into the T. And the reasoning behind that is if we do not have, if we've got a longer run there, we can have water lay in there between cycles. And when steam comes down, some steam will come down that equalizer line. It'll pick that water up and just start hammering it. And that'll usually, you'll hear that type of water hammer on the startup cycle. So that may be the first thing to look for, is the Hartford loop. If they don't have a close nipple or a street elbow, you will get hammer, and that is not a lot of fun to deal with. All right, so that's the near boiler piping for steam up. So the steam flow in the header should always be in the same direction. Multiple supply risers should combine before the supply main is taken off. So we want to make sure that all the steam is flowing in one direction. So again, this is where we have two risers flowing against each other. And this, we don't want to crash the steam flow from two risers into one supply outlet, because as they meet and combine, as again, you remember, this is coming out at coming out at 1,700 feet per second in both of these risers and running into each other here. And when that happens, again, you'll get that wet steam going out to the system. And the same with this, don't use a bullhead tee when the flow is from a branch tee to a run. So on the equalizer line, you want that takeoff to be here and then go to the equalizer line. So Larry, this is our third question. It's back to you.
Okay, go ahead and, oh, is that the question right there? Okay. All right,
Well,
my
that's
bad.
the answer to the question.
That's the answer to the question. All right.
Yeah.
Well, let me share that screen with you here real quick. Where is it? Not finding it here. Okay. Give me 1 second here, guys. There it is. Okay. Question number 3. On a boiler with 2 steam risers going to the steam header, the system supply takeoff should be between the 2 risers. The answer is obviously no or false. I can't remember how it looks on the test,
It's
but
no.
that I think it is no. So there you go. That's the third question. Make a note of that because you're going to need it in just a few minutes here. Okay. Let me unshare that, and I think you are back in the driver's seat. And just once you get to your screen, just hit PowerPoint and Shift F5.
Okay, so we are back. So again, don't crash the steam flow because you'll get wet steam going out. And don't use a bullhead tee to connect to the system and the equalizer. Those are 2 separate takeoffs. We come out from the 2 risers. We go to our supply line header and then to the supply to the system. Then we would continue on to create the equalizer line. So now we're to air out, because as I've said many times throughout this program, steam will not go where air is. It cannot occupy the same space. Therefore, air must be vented before the steam can enter. An air buildup causes back pressure that will shut off a burner. And then obviously that's the same as going off on low water. We are not completing our cycle. We're not getting good steam out to the system. So venting should be done at a rate that does not create any back pressure on the boiler. So again, if we have a really long run of main in the basement, and we're having issues, the boiler's going off on low water before it's going off on limit, we may need to look at the vent. It may be missing or blocked, or we may just not have enough capacity. So we would need to create a tree here. So you would come up here, you come up with the tapping, come out of the tapping with a nipple, go into a T, and you can come out either side of the T and put vents, which is called a tree. You want to put a tree out there then you can continue that on if there's many vents on there. The faster you vent the air, the faster the steam gets out to the system, and the better chance you have of all the rooms in the house heating at the same time and the same rate. So venting needs to be done both at the radiation and the ends of the main. For 1 pipe work, vent the supply main, while for 2 pipe work, vent both the supply and the return mains. The ideal air vent, if on the radiator or the piping, will eliminate air from the system at the rate consistent with best results. So again, going back to those, if you go through a house and you see that say it's got 10 radiators and 4 of them have the number 40 Hoffman vent, which is a non-adjustable vent. And then you have the other 6 radiators have the 1A adjustable air vent. Then we're not getting a balanced flow through through the radiators. So ideally, we want the same vent. We want them all to be 1As, or we want them all to be number 40s, so that they vent at the same rate, so we get consistent results throughout the system. Okay, following the path of air. Air in the near boiler piping and the supply mains is forced to the end of the steam supply main by the flow of the steam. As we've learned, air typically leaves the supply main through the main air vent. Air can also pass to the dry return on two pipe systems by a radiator trap installed above the main. That is what I was talking earlier when we were looking at the thermostatic traps. It's called a crossover trap. So again, we're down at the end of the main. We're venting air to the return main so we can vent out quicker and we can get the air out of the steam main faster. And that would allow the steam to travel to the end of the main quicker and feed all of the risers to the radiation in hopefully an even rate of flow. The end of the supply main F&T traps can be used to pass air to a vented condensate, boiler feed, or vacuum unit. In really big houses, sometimes you'll have end of mains and they will dump them into a condensate transfer unit. And then that condensate transfer unit operates on a float, like the floating thermostatic trap. When the condensate transfer unit fills up with water, the float rises and activates the pump and sends water to the boiler feed unit. Quickly, you do not want to use a condensate return unit to feed your boiler. You need to have that boiler feed unit. You need to have a control on the boiler that will activate the pump. You do not want that pump to come on based on a float in the tank because it could flood the boiler if you do that. So you probably won't ever see that. I've seen it on one system and somehow it works. Well, it hasn't worked. The guy's had to replace some sections because he had condensate return issues, but he didn't want to repipe the whole building or the whole system. So that's the only boiler I've ever seen with a condensate unit on it, and it doesn't work. But the owner wouldn't believe me, so I stopped trying to convince him. And then we go for water back. Obviously, that's critical too. We need to we can't produce steam in a boiler to heat without water. So the water has to be returned from the system to the boiler before the burner shuts off due to a low water condition. So that's what I was saying. The ideal cycle of a steam boiler is one that goes off on the limit control, where we've reached 1.5 pounds of steam and everything is satisfied, as opposed to going off on low water because we have clogged returns. So again, is not the ideal boiler run cycle during a call for heat is the one that's not interrupted by the low water cutoff. And again, if that's happening a lot, here is most normally, this is, I would say 80% of the time, the culprit is a clogged wet return. Hopefully the returns have unions on them that you can, shut the boiler down, crack a union and take a look inside or see what kind you can crack it during operation too. Just obviously before the start of the operation, you would crack it, start the boiler to operate and see what kind of return you got coming back through that return line. Not the ideal way to do it, but it can be done that way. Okay, so we got to try and follow the water back. Water in the mains flow back to the wet return. Water in the radiator flows through the trap or vapor device back to the dry return, and it carries condensate from the radiation down to the wet returns. The water in the header is carried across the main and drops down into the wet return also. The wet return collects all of the condensate from the system. Water in the two pipe radiator flows back to the dry wet returns through traps. Water separates from the steam in the header, flows back to the boiler through the return equalizer pipe. So again, that's why it's critical to size this header so that we're getting proper steam flow, so that just a little bit of condensate condenses. And also, if you go into a steam boiler room in anyone's home and none of the supply lines are insulated, I would highly recommend that you insulate all of the supply lines that will have steam in them. It's not necessary to do the return lines, but if you don't have it, some of our, you need fresh air to combust boilers. So if you've got cold air in the basement or the boiler room, it will condense that steam much quicker, and chances are you'll go off on low water as opposed to a limit control. So depending on the pitch, in a one-pipe steam system, water in the runouts will flow back to the supply main or out to the riser in the drip. Wet returns collect all the condensate to return directly to the boiler and directly through condensate boiler feeder vacuum pumps. Again, wet returns critical, as well as the gauge glass is giving us good operating characteristics of the boiler. Okay, that is pretty much all I have. Do you have any questions?
There was just one said,
Okay.
want to know if you would talk anything about uh, pigtails on pressure gauges and
Okay.
controls, and a little bit about the controls for the steam.
Okay.
Okay.
Yeah, the two controls that what you generally do, you'll come out and you would come up. You'll have a tapping on the boiler that you would bring a pipe nipple out, and you would go into a T. But before you do that, you can do it one of two ways. You can either come out of the boiler, go up, over, and down, and then just run a T, and then run your operating controls off of that T, because that coming up, over, and down has created that pigtail. Uh, so it'll stop the steam from reaching the controls. That's what the pigtail is for. You can come out of that boiler, go into just a standard T, come out of either side of the T, and then go into two elbows coming up, then put your pigtails into that elbow, then mount your controls on top of that pigtail, your high limit control and your operating control. And that's a PA 404A is the normal, PA 404A 1033 is the normal operating control and high limit control that are shipped. And the reason you use the pigtail is to keep steam from the boiler, that because this tapping is going to be above the water line. So you're going to have steam coming through it, which the control needs to see the pressure to operate correctly, but it doesn't need the live steam to actually hit the control, because it would affect the control. So you'll come out of your boiler, you'll go into a T, you'll go into two elbows, or a T with another, and then come out of that with another elbow. If you have multiple controls, some boilers have three controls on them. But you would come out, you would go into the pigtail, and the curly Q of that pigtail is what traps the steam, doesn't allow the steam up to affect the operating control. And the pressure control, the PA 404A 1033, which is the most common control that comes with boilers, generally has a half pound to a 9 pound setting on it. It's an actuated high limit safety control for steam boilers. It makes at a set point, which is usually a half pound, and then breaks at a set point plus the differential, which is 1 pound normally, to make up for that the way they designed the steam systems back in the day. So you'll have a half pound cut in, a pound and a half cut out. And those pigtails are critical to keep your operating controls from seeing live steam and malfunctioning. So that's why the pigtails are used, or a up, over, down, and then out, and then up again to the controls as an option to not having pigtails. Does that answer your question?
Well, we don't know, but
Okay.
I'm not seeing any nods, so we'll
Okay.
just everything's going one direction here. But I did have a second question, and
Okay.
that is, what dictates a cast iron versus a rolled steel condensate tank?
That's a good question, and I don't really have a good answer for you. They make the condensate transfer units, what's called, Hoffman calls them a Watchman unit, that just operates on the float level. Those are normally cast iron. Uh, what I can only thing I can think of why they go with steel on the boiler feed units is that if we do get live seams somehow coming back to it, the steel tank will hold up better. Because as I said, the cast iron boiler or the cast iron condensate transfer unit is cast iron like the cast iron section. So if we get fresh water coming back through that for some reason, I guess it could, or, we've got the incorrect pH of the water or whatever, it could wear away the inside of the condensate unit. And maybe that's why they go with steel. That's really the only thing I could really think of. Probably also because steel is cheaper to manufacture than cast iron. And if you're familiar with any manufacturers, they're all about the bottom line and they're trying to keep it as inexpensive as possible to produce their product. So steel tends to be easier to work with and easier to, it'll last. It can last better with live steam encountering it. I guess is the
How
best.
about the low water cutoff? The question is should the low water cutoff be cleaned on an annual basis?
Okay, that is a good question, and it has taken me 30. Okay, Weil McLean has always said that once your steam system is filled up, you should not be introducing any fresh water to it, and that you will lose roughly a half a gallon a month through air vents. So I was okay with that. But then in talking to the McDonnell Miller people who produce the low water cutoffs, they told me that they want their cutoffs, low water cutoffs and low water cutoff and pump controls, they want those blown down weekly during the heating season. So I had a hard time reconciling my boiler manufacturer telling me not to add water and the control manufacturer telling me to blow the controls down, which is going to add fresh water. So after beating on Weil McLean, and they will not put this in writing, but I finally got an engineer to admit that, and this is generally on LGBs where you see it, that the Weil McLean cast iron sections can handle up to 2 gallons a week of fresh water. And on an LGB, you'll have two controls. One is a primary low water cutoff and pump control, and it's mounted about 2 inches above where your secondary low water cutoff is. So for some reason, this primary low water cutoff fails, we have that safety secondary low water cutoff. So what they told me is it'll take 2 gallons a week of fresh water. So when you go to blow those controls down, each one of the bowls on those controls is generally about a half a gallon of water. And the way you want to blow that control down is you have a ball valve on the bottom of it. You open that ball valve till you see clear water coming out, and then you close it. That'll give you about a half a gallon. You just want to basically exchange the water in the bowl. You just want to drain that, and then it'll fill up from the system again. And if you open it up and water comes out, close it up, and you're good to go. If you open it up and it's a trickle or nothing's coming out, then you know you got an issue. You need to shut that boiler down, open up that control, and chances are it's full of mud, which is not allowing the float to rise or fall, and that can be an issue. So a lot of times on those types of boilers, I recommend putting either on a residential job that doesn't have a boiler feed system or doesn't use that primary low water cutoff and pump control to operate a pump. It just has a standard low water cutoff. I recommend using a feeder. We sell the hydro level, I think it's a VXL 24 volt, and it has a water meter on the feeder valve. So you can look at the control. What you do is you put that on there and you run the boiler and you go back in a week. If you see that water meter has added 10 gallons of water, then we know that we've got an issue somewhere that we're not getting condensate back and we're adding fresh water to the boiler. On the bigger ones, what you would want to do would put just like an inline We get them from Norgas. They're called the Versa Mag, something like that. It's just a standard 3/4 cold water inline water meter to do the same thing. And you would tie that on the city water line going to your boiler feed tank. So again, you would check that after a couple of weeks. If you got 30 gallons already put into that boiler feed tank, we got issues with condensate return. I hope that answers that question.
I think we're good. All right, that was the last question.
All right.
I think thank you, Jeff. It was good. It was a very good class, and we thank you for that.
I
Let
hope you
me.
guys learned something. And again, if you need any information, anything that we showed on this, I'm sure Larry can get it downloaded and get
Thanks,
it to you if
Jeff.
you need. You're welcome.
All right. Thank you, Jeff. Yeah, it was a good class as always. All right, I'm going to take the wand away from you. And all right, guys, here's what's going on now. I'm going to be sending out an email, but before we do that, I just want to let you know that the email that I'm going to send will have the link for you to do the answers, the verifications for those of you that need hours or want a certificate. I think some of you are watching this in a group, like at Stormer Anderson and over at Comfort Systems. So you guys, I guess somebody has logged on. Whoever's logged on is going to get the email. Okay, now also I want to tell you that in the email, I've attached links to a couple of the documents that Jeff was talking about. One of them is called the radiation reference tables. That's a PDF that you can link from the email, and also the STEAM glossary of terms, which is kind of nice. They're very small documents, but it'd be nice to have, and it kind of is a nice cursory thing about the class that we just finished. Okay, I think that's it. Okay, I'm sending out the email. I'll do it right now, and once this is okay, it's gone. Once it's you guys, I'm going to leave it up till about for about 30 minutes. So you got 30 minutes to go in and take care of business, and we look forward to seeing you all again next time. Thanks for a great class, Jeff, and thanks for all you guys for coming. And for all you veterans out there, thank you for your service. Really do appreciate it. From on behalf of Winstone Controls, let me just say goodnight.
Thanks a lot. Great job.
Thank you.
Thank
Thank
you.
you.
See you, Larry.
All right, Jeff. Thanks again. Good job.